Okay, so thank you. Thank you for being still here or online. And what I'm going to present is essentially the content or a summary of the content of the PhD of Kevin Atsu. And it is worth bringing it out the fact that this work has been done in tight collaboration with a team of biologists from Sophia Antipolis and Nice, with Fabienne Anjuer and Véronique Brou. Okay. So they really invested in the collaboration and in the mathematical framework and in the modeling of the phenomena they are interested in. So let me start with a summary of the talk, what I want to describe. So we will play with a multi-scale PDE system where we will have two length scales, a scale which describes the size of the tumor cells. Okay, it describes how the tumor is growing. It will be denoted by Z later on. And a space variable because we want to take into account the displacement of the immune cells towards the tumor. Okay? And this displacement will be driven by two phenomena, by a natural diffusion in any direction, and this is coupled to a chemotactic mechanism which drives precisely the immune cells towards the tumor. And what we found is the fact that there is an equilibrium state, and this is really surprising because we made nothing in constructing the model to build into the equilibrium. Okay? This is something that we observed at the end. We just translated into equations the phenomena the biologists wanted to describe, and running the simulation, we observe this equilibrium. And what is remarkable is that this equilibrium describes a state where the tumor is under the control of the immune system, but it remains a tumor. The tumor is not completely eliminated. It remains a residual tumor that we want to investigate and to describe in further details. And what is also interesting on the mathematical viewpoint is the fact that this equilibrium can in fact be described by means of an again problem. And this opens the door to further investigation of the property of the equilibrium by making a direct simulation that avoids to run the full time evolution problem. Okay, next I will be a bit fast about this, but you can also add some phenomena into the model to make it more complex by adding some pro-tumoral effect of the immune system. At some point, not in the earlier stage of the tumor growth, but at some point the immune system starts collaborating with the tumor. And if we add such effect, we go to another phase, which is the escape phase, where the tumor grows without any control. Doing that, we can investigate the role of different parameters into the models, so the division rate, the growth rates of the tumor, the conversion rate from resting immune cell into active immune cells, and we can make a hierarchy among these parameters, and that can be an help to design a better treatment by identifying the most important parameters in the shape of the equilibrium and to target these parameters. Okay? And we were also very interested at the beginning in the role of the space inhomogeneities, because there are plenty of models dealing with this situation with ODEs, but we wanted to use PDEs precisely because we were interested in the influence of space organization. Okay, and just to continue in the motivation, this interaction between the immune cells, the immune system, and the tumor growth has been bring out at the beginning of the 20th century and the middle of the 20th century by saying that some tumor appears and they activate the immune system that can detect these tumors and eliminate the tumors. Okay? And certainly these reactions are below any detection threshold, so maybe we have some tumor at some point, but just detected and eliminated and nobody knows that there is something bad somewhere. So the theory has been more advanced, more developed since then, and now someone which is very famous in this field is a paper of Dunn, Holt, and Schreiber, and they identify the triple E phases. So the triple E means elimination phase, where just the immune system detects the tumor and eliminates it, and that's it. The equilibrium phase, which is exactly what we will be interested in the talk, which is described by the picture that you have on the right, that I will comment in a minute. And then the escape phase, where the tumor can grow without any control. Okay? And again, it is possible that this equilibrium is below the detection limit. And the challenge is precisely after a surgery. Very likely you cannot eliminate with the surgery all the tumors. It remains some cells somewhere. And the challenge is to predict what will be the future of the small tumors below the detection limit that remains after a surgery. Okay, so here you see that after a simulation what the model does. So in red, this says the mass of the tumor. And in blue, this says some averaged concentration of immune cells. So you see that you have some oscillation at the beginning, but the two quantities converge to a constant state. If you look on the red curve, you see that it converges to a value which is strictly positive, so it means that it remains a residual tumor at the end. The tumor is not completely eliminated. And here there is a dotted line for the concentration of immune cells, because we can predict the asymptotic value of the concentration of immune cells, and the model does what you can guess theoretically. It converges to the predicted value. Okay, so here again, this is another picture to illustrate what we want to do. You have the three phases. The elimination phase, you have a tumor that appears somewhere. It is eliminated, it tries to grow again, and it is eliminated again. And at some moment, you have the establishment of some equilibrium where the two quantity remains in a constant state. The tumor is under the control of the immune system. Okay, so this is what we want to describe. But then this is here the situation where only the immune system is acting against the tumor, but at some point it collaborates with the tumor, and when you add this phenomena, you go to the escape phase where the tumor mass is just growing and without any control. So in doing that, you can play with the parameters and make a hierarchy appear between the role of the parameter on the mass at the equilibrium. And this is what we want to describe, to target with treatments, the most efficient treatment to make the residual tumor in the most variable state for the residual tumor. Okay, so let's enter into the details and into the equation. So here, this is a few warnings about the talk. So of course, you need to neglect many phenomena, and you need to adopt a certain modeling viewpoint. And this has been very difficult in the dialogue with the biologists, because it's difficult for them to make a hierarchy appear and to say that you can just disregard some phenomena. They want to keep everything, and that could be difficult to do mathematics and to do simulation. So I adopt also some modeling assumption. You can discuss everything, of course, and do another model to describe the same situation. Okay? What is important is to keep in mind that simplicity is very important, because if you add further phenomena, it's always doable to add a term in the equation, but at the end what will be difficult is to assign a numerical value to the phenomena that you want to enter into the equation. You want to enter a reaction with a certain chemical substance. What is the rate of this reaction? Okay, and it's very difficult to have this value. And it's very difficult to design an experiment to identify this value. One of the difficulties is the fact that we have some data, but we do not have time evolution of the data, because either we kill the mice or because we remove the tumor, and we do not know what will be the evolution. Okay? So this has been a real difficulty. So we want to keep the model as simple as possible, to have a few parameters which remains unknown and that need to be identified by numerical procedures. Okay, as I said, we were interested also in the role of the spatial effect. So this is why we worked with the PDEs instead of ODEs. This is a model which is also designed specifically for the earliest stage of the tumor growth. Okay, as I told you, we concentrate on something which is certainly below the detection limit. And this is very just limited to the earliest stage. For later stage, we need to switch to another model and to consider something more structured in space, for instance. And also, I noticed that some of you are specialized on several types of cancer. You know much more things than me. So here, what I want to describe applies to cutaneous squamous cell carcinoma, and maybe not to other types of cancers. Okay, so for the talk, you need to keep in mind this picture. I think it's large enough. So we have two length squares in the model. So the tumor is located at the center of the domain. Okay, so this is the point here in the middle. It's the tumor cells. And the tumor cells are changing their size by natural growth and by cell division. Okay? So we have a variable which identifies the size of the tumor cells. This is variable z. And this variable z is distinct from the space variable, which is the variable x, because we assume in this modeling that the size of the tumor cells is infinitely small compared to the length square of the displacement of the immune cells. This is why we have two length squares, which are distinct. And so you see the immune cells like the spots in gray on the picture. So you have some pools of immune cells, which are just sentinels, which are resting immune cells that need to be activated to fight against the cancer cells. Okay? Once they are activated, they move by diffusion in any direction. So we have some wavelets starting from the spots. And we have also a directed motion that drives the immune cells towards the tumor to kill the tumor cells. Okay, so the two quantities of interest will be the concentration, the distribution in size of the tumor cells, so n of t and z. So if you integrate this quantity between A and B, you obtain the number of tumor cells with a size between A and B. Okay? If you multiply by z, you take the first order moment of this quantity, you will get something which is homogeneous to the mass of the tumor cells having a size between A and B. So this is the first unknown. And the second unknown is the concentration of immune cells that will be denoted C of T and X, which is resolved by space because they will move by diffusion and chemotaxis. Okay, so now let's write the equation. So I start with the equation for the tumor cells. So some of you perfectly know this kind of equation. So we have first a natural growth of the tumor cells, which is described as some quantity V, that will be constant for the simulation. So maybe it's much more realistic to work with a Gompertz growth rate. But again, if you make the growth rate more complex, you need to identify more parameters to make some simulation that could be useful in practical situation. So maybe this growth rate could be dependent on the size, but for the simulation here it would be constant. Then there is also a cell division mechanism. You just cut a cell with size z into two pieces, a cell with size z prime and a cell with size z minus z prime. So sorry, I inverted the with respect to my slide. And the cell division mechanism is described by two quantities. A division rate, which is A, that can depend on the size. For instance, you can imagine that when you are looking at very small cells, they cannot divide. So maybe this quantity A of z is 0 when z is small. Okay? And then you have a kernel that tells you how you distribute the cells when you cut the cells into two pieces, how you distribute the two pieces. So when we completely negate all the interaction with the immune system, that will be written later on, we obtain this equation for the evolution of the tumor cells. So on the left of the equation, you have just a transport term in the space of size, okay, just due to the growth rate V. And on the right-hand side, you have the cell division mechanism, which is described with the operator Q of n. So here you make the balance. You are counting the cells having a size z after the division. So you are losing cells with a size z because they divide. This is the meaning of this loss term here. And you are gaining cells with a size z because of the division of cells having a larger size. Okay, so this is the meaning of this integral that starts from z as a lower bound of the integral. Okay, so this is the cell division growth and division equation. And for the simulation, I will just focus on the case of the binary division, where you have a cell that you cut in two equal pieces, and the expression of the Q and N is just written in the slide. Okay, this is a typical example of this operator Q of N. Okay, so now let me write the equation for the concentration of, sorry, I need to bring out a few properties of this operator. And the first property which is important is a mass conservation property. You divide a cell into two pieces, but if you add the mass of the two pieces that you have created, you obtain the mass of the mother cells. Okay? So this is written here as a property of the division kernel K. And it tells you that if you take the first order moment of Q of n, you will obtain 0. So the division mechanism does not change the mass of the population. But it creates more cells. If you just cut all the cells into 2, you will have twice the number of cells at the beginning. So you denote n of z this integral. And if you just integral Q, you obtain something which is non-negative here because you are increasing by division the number of cells. Okay? So the division mechanism keeps the same mass but increases the number of cells. So this leads to introduce two quantities, two macroscopic quantities if you wish, which is the total number of tumor cells, so this is just the 0th order moment of n, and the total mass of the tumor, which is the first order moment of n. So if you look at the evolution of these two quantities, for the total number of cells, this is a non-decreasing quantity, and it increases because of the division mechanism. Okay. And for the total mass, this is also a non-decreasing quantity, and the fact that it can increase is due to the fact that you have a growth rate, but it has nothing to do with the division mechanism. Okay. And so this is a combination of the two, division and growth, that changes the mass and the number of cells. Okay, so now let's switch to the other population I'm interested in, the population of immune cells, which is denoted C of T and X, which is structured by space. And you have several mechanisms to drive the evolution of this quantity. The first one is, as I told you, you have some reservoir of immune cells which are inactive, which are in a naive state, and they need to be activated by the presence of the tumor. Okay? So these immune cells are the natural killers of CD8 plus T cells, for instance. So they need to be activated to be able to fight against the tumor. So this tells you that you have, in the right-hand side of the equation, a source term. So this describes the reservoir that could be located in specific spots. And the activation depends on the total mass of the tumor, mu1, through a certain function g. There is also a natural death of the immune cells. And for their motion, the motion is driven by natural diffusion, so in any direction. And you have also a directed motion due to a certain potential. So this potential is denoted by phi, which satisfies the diffusion equation. Okay, like the Poisson coupling for people who are used to Vlasov-Poisson equation, for example, this is exactly the same mechanism. You have a certain form function sigma, which is located at the center of the domain where the tumor is. And the strength of this potential directly depends on the mass of the tumor. So you just should think of the potential like that. So a set of arrows pointing towards the tumor, towards the center of the domain. And the strength of the arrow depends on the mass of the tumor. The larger the mass, the stronger the arrow. Okay, so I describe everybody. So in the initially you have a certain concentration of immune cells, and at the boundary of the domain you have no active immune cells. You are far away from the tumor, and there is no reason to find active immune cells far at the boundary of the domain. Okay, so the activation from the pool of resting cells, the diffusion mechanism, and the chemotactic mechanism that drives towards the tumor. So now let me write the full coupling between the two populations. So I rewrite first the equation for the tumor cells, but now I take into account the effect of the immune cells on the tumor cells. as I told you, the immune cells are killing the tumor cells. So this is a death term, which depends directly on the concentration of immune cells, with a kernel delta, which is naturally concentrated next to the center of the domain, next to the point where the tumor is. Okay? So this is not a delta Dirac, but a very peaked Gaussian, for instance, at the center of the domain. Okay, and this has a two-way coupling. So the immune cells are acting on the tumor cells by killing tumor cells, and the tumor cells are acting on the immune system by activating, on the right-hand side, the immune cells, and by driving the strength of a chemotactic force. Okay? And the mu1 is the first order moment of the concentration, of the distribution of tumor cells in size. Okay? So this is the model. I told you it's as simple as possible, but it's already complicated. We have two PDEs with different set of variables, T and Z for the tumor cells, T and X for the immune cells, and we have a nonlinear coupling in different places of the model. Okay? Okay, so we can play with several parameters into the model, and you can distinguish the action of these parameters depending whether they are related to the aggressiveness of the tumor, which is the case of the growth rate of the tumor, the division rate of the tumor, and also the death rate of the immune cells. That can be also influenced by the presence of the tumor. Okay? So this is a first set of parameters, and the other set of parameters can be related to the efficacy of the immune response. So this is the case of the conversion rate of the resting immune cells into active immune cells. This is what I call G. The strength of the immune effect, how much the immune cells are able to kill the tumor cells. The strength of the chemoattractive force, okay, the strength of the arrows pointing towards the tumor, and the diffusion coefficient D. So here, for all the simulation, I will play with the constant diffusion coefficient D, but something that has certainly a role that could be important is the fact that depending on the tissue around the tumor, maybe the diffusion is not efficient in the same way in all the directions. So you can incorporate some direction mechanisms by playing with the diffusion coefficient. Again, due to a lack of data, we just play with a constant coefficient. Okay, just to start with, to understand the role of the different parameters of the model, you can make the model even more simple than that. You neglect all the space dependence. You assume that all the coefficients are spatially constant. You replace the Dirichlet boundary condition by a Neumann boundary condition, and you can integrate the equation and obtain a closed system of equations. So if you do that, you obtain a system of ODEs, which is very simple. The unknown of this ODE system are the total number of tumor cells, the total mass of the tumor, and some mean value of the concentration of immune cells. Okay, so you have a 3x3 ODE system. And the first game is to identify the equilibrium state of this ODE system. And in fact, you observe, which is quite common in ODE system in biology, that you have two distinct equilibrium states. The first one is the healthy state, where you have no tumor cells and no immune cells. But it turns out that this healthy state is unstable, linearly unstable. And you can identify an unhealthy state where you have positive concentration for all the population, and this state is linearly stable. And you see also, looking at the eigenvalues, that you have an imaginary part when A, the division rate of the tumor cells becomes large, so it may appear some oscillation in the next to the equilibrium state. Okay? So this is just to understand the meaning of the model and the role of several parameters into the model. And then we go back to PD. Is that okay? Or? But before going back to the couplet system and to the PDE, I want to make a parenthesis because I will focus on the large time behavior of the system, and I want to show you why I can guess what is the asymptotic behavior of this very complex system of PDE and why it is related to an eigenvalue problem. Okay? And to do that, let me go back to a basic of your background on mathematics. This is a Perron-Frobenius theorem. So the statement is written on the screen. So you start with a matrix with all the entries which are strictly positive. And then you know that the spectral radius of the matrix is an eigenvalue. And what is remarkable is not only it is an eigenvalue, but the associated eigenvector, you can find an eigenvector with all the entries strictly positive. Okay? So this is more or less what is written there. And you can play the same game with the transpose of the matrix. And this statement of linear algebra is important to understand the large time behavior of differential systems. So I consider the differential system driven by the matrix A. And the first remarkable property is the conservation property. So you conserve this quantity. And this is a very simple computation. You take the time derivative of exponential minus rho t and the inner product of x of t with phi, which is the eigenvector associated to the transpose of A. You take the derivative of that, so the exponential is in factor. The first term corresponds to the derivative of the exponential, and the other term to the derivative of x. Then you remember that phi is an eigenvector for the transpose of A, and just by transposing, you see that you obtain 0. So you have something which is conserved. The second remarkable property is that you have something which is dissipated by the model. So you look at this kind of L2 norm, you can say that it is also an entropy, and this quantity is dissipated. And again, this computation is quite tricky, and it uses the fact that you have eigenvectors. So here I reproduce the computation for you. You take the time derivative of this fancy quantity. You have to take the derivative of the exponential and the derivative of the xi of t. Okay, so the first term gives you this guy, and the derivative of the xi gives you this part. And now for the red term, the term that comes from the derivative of the exponential, you can write it in two different ways, depending if you remember that phi is an eigenvector of A transpose, or if n is an eigenvector of A. Okay, so you have two ways to write this product. So you use the two ways in this way. So you replace the red term by a blue term plus a green term. And in this one, you just change the role of ing, and you end up with this expression where you recognize a square. Okay? So it precisely tells you that something is dissipated. So something is conserved, something is dissipated, and this allows you to identify the large time behavior of the population driven by the differential system. And as time becomes large, x of t behaves like exponential minus exponential rho t, so there is an exponential growth of the population. And you have also a profile, because the profile is proportional to the eigenvector n. Okay? So you perfectly know what is the asymptotic behavior of the population. So once you have understood how it works with matrices in infinite dimension, you can adapt the argument working with differential operators or integral differential operator. And in particular, it applies for the growth and division equation that I wrote before. Okay, so you just have to replace the finite dimensional framework by a compactness argument. And it turns out that as time becomes large, the distribution function n of t on z, which is driven by this equation, is given by this behavior. So again, an exponential growth rate driven by a certain eigenvalue, and a profile n of z, which is an eigenfunction associated to rho. Okay, so the eigenvalue problem that you need to solve is this one. So the theory that tells you to tell that there exists a solution to this eigenvalue problem and that the asymptotic behavior is indeed this one is due to Baccelli, Pertam-Ritschik, Michel, and Domingue-Gabriel for the most advanced version as far as I know. Okay? So this is just for the growth division equation without any coupling. Okay? And you have some formula in the case of constant growth rate and for the binary division operator. And what you get is that. So the profile is driven by the ratio between A and V, the division rate over the growth rate. If this ratio is small, you have something which is peaked for small size of the cells. When this ratio increases, you spread the profile and you obtain this curve, for instance, which is here. Okay? So you have explicit formula in the simple case. Okay, so now let's go back to the couplet problem. Okay, so I remember you that it is written in this way. So you have a coupling from the def term on the tumor cells, the activation of the immune cells, and the chemotactic force. Okay? And you know that for the first equation, if you remove the action of the immune cell, you have an asymptotic growth rate, which is exponential. And the idea is that the action of the immune system will be to counterbalance this exponential growth. Okay, this is what you expect. So in other terms, what you expect is that asymptotically nothing will depend on time. You will obtain a stationary state. So a stationary equation for the concentration of immune cells that depends on a parameter mu1, and the parameter mu1 that will be the mass of the tumor for large time is chosen such that you realize this constraint, okay? Which is precisely to say that the death rate of the immune cells acting on tumor cells coincides with the leading eigenvalue of the growth division equation. Okay? So that you will obtain in this way. Asymptotically, this right-hand side should be 0. Okay, this is what you expect. And there is a theorem that tells you this is not completely silly. At least when the target is small enough, you can indeed find a value mu1 which reaches the target, which reaches the constraint. Okay? And this is a drawback of the theory. The proof is based on the implicit function theorem, but I am not able to go beyond the smallness condition. Okay. And I am not able to prove that the asymptotic behavior. This is what I observed numerically. Okay, so let's go to numerical results. The formation of the equilibrium, which is, I expect that is driven by this eigenvalue problem, is something which is very robust as far as the distribution of the resting cells, the pool of immune cells which are inactive, is space homogeneous. This is something which is very robust that you observe in all the simulation. So this is relevant when the immune cells you are considering are the natural killers because they are almost everywhere in the body. And what you observe is that fact that the mass of the tumor cells tends to a constant. The average value of the immune cells tends to the leading eigenvalue of the growth division equation. And the distribution in size of the tumor cells is proportional to the eigenvector of this equation. Okay, so here are a few numerical results. I'm just changing the division rate of the tumor cells between all the simulations. So here you have a damping which is very fast towards the equilibrium. Here you have also a damping which is maybe not as fast, but which is quite good. Here we are converging towards the equilibrium. For the immune cells, the concentration converges to the expected value, but we have oscillation that appear, and the oscillation are more present when you increase the size A, which coincides the observation that we made on the system of ODs. Okay. Of course, you can also remark that the scale is different here, and the mass of the tumor is also larger when you have increased the aggressiveness of the tumor. Okay. So this is in the case of homogeneous distribution of immune cells, of resting immune cells. This is a bit different when we are playing with a distribution of immune cells which is non-homogeneous. So this is a case where we are looking at the T cells which are just stocked into the draining lymph nodes, and they need to be activated and to move towards the tumor. Okay, and what we observe is really different. We observe some kind of periodic patterns, something that looks periodic, with spikes and remission. So here are the numerical results. So when A is small, you have still the damping as before. When A is increasing, in the case of non-homogeneous distribution of immune cells, we have this apparition of peaks and remission phases that looks really periodic. So in fact, we have a damping but on a very, very large scale of time. Okay? So maybe it's not reasonable to wait for the equilibrium state. Okay, so this is the comment that I really want to make, because I told you that I have in mind a theory. I'm not able to prove the theorem, but what I have in mind is the fact that there exists an equilibrium state for any eigenvalue of the growth division equation. And I have in mind that certainly the solution converges to this equilibrium. I'm ready to bet for that. But what does it mean? Maybe this is completely useless, and maybe this is absolutely nonsense. And this is illustrated by these pictures. So here, this is the ideal case where you are converging to the equilibrium, maybe with some oscillation, and the value of the tumor mass is not that high. Here, we have this kind of periodic pattern, at least on the observation time length, and the equilibrium appears on a very, very large scale of time. So it's not reasonable to say that you will observe the equilibrium. What you observe is the peaks. Here the situation looks better with respect to the theorem. We are converging to an equilibrium. But if you look at the value of the tumor mass in the transient state, certainly the model is completely wrong in this range of value for the tumor mass. And certainly the guy is dead. Okay? So maybe you have a theorem, but the theorem has absolutely no meaning. Okay, this is for the critical about the results. Nevertheless, let's try to use what we understood about the model and try to focus on the property of the equilibrium state. Okay? Because we have this interpretation of the equilibrium state by means of an eigenvalue problem, we can perform some computation by using this viewpoint, avoiding the simulation of the time evolution problem. Okay, and we can predict what will be the equilibrium state from scratch. So the idea is the following. We compute the eigenpair for the cell division operator, the eigenpair we are interested in. So if you go back to the proof of the for the growth division equation, you need to introduce a shifted operator. So you need to shift the operator with some lambda, and lambda should be chosen large enough. And then you invert this operator and you look at the largest eigenvalue of the inverse operator. Okay? And the question for numerical purpose is how large you need to shift the operator. So for the continuous operator, you have some estimates, and you need to check that the discretization does not pollute this estimate, and you need to know where to find the largest eigenvalue. Once you have understood that, you just run your power algorithm to find the eigenstate. And then, to play with the coupling with the immune cells, you can use, for instance, the dichotomy method or the Newton algorithm, as you wish, to find the value of mu1, the tumor mass, at equilibrium. So it turns out that this is a very efficient method, which provides a good agreement with the large time simulation of the couplet system. So here, this is a few results. So here you have the mass when running the evolution problem. Here with the power algorithm, the dichotomy method, and you see that the error is not that bad, okay? 10 minus 16, 10 minus 7. So it is worth, if you are interested just at the equilibrium, not to run the evolution problem, but just to use the eigenvalue interpretation. The interest in this approach is the fact that you do the simulation very fast, and you can run many simulations playing with plenty of parameters. So you need to sample the parameters according to certain biological value that you have. So this is what we did. So there is a part which is a bit tedious and difficult, is to identify some parameters. So we knew some of them, but some of them remained hidden. So we need to find some way to identify the missing parameters. And then we perform a sensitivity analysis to identify the most important parameters in the value of the tumor mass at equilibrium. So it turns out that the leading role is a strength of the immune system. What is also interesting in the conclusion that we obtain is that it is very interesting, very performing to couple two ways to act on the equilibrium. So this is illustrated by this picture. So here in abscissa, I played with the division rate of the tumor cells. So when I decrease the division rate, I decrease the mass at equilibrium. Okay, so this is a way you have maybe a treatment which reduces the division rate of the tumor cells. But you can play also with the strength of the immune cells, and it is interesting, as you can see on the picture, to play on both. And maybe this is also important because maybe one of the treatment has some toxicity, and if you reduce the dose by playing with the dose of another treatment, you can have something much more efficient. Okay, so now let's switch to make the model a little bit more intricate. So I will not write the equation, okay? I just want to give you the flavor of what we did to make the model more complex, more accurate, and to take into account the pro-tumoral response of the immune system. Okay, so here you have the tumor cells, and what we did so far is to play with the left-hand side of the picture. So the tumor cells activate the anti-tumor immune cells. Okay, they activate the cells that become active, and they are also activating some chemotactic potential, which says, hey, come on and kill the tumor cells which are here in this location. Okay, so this is what we did: directed motion, and the anti-tumor cells kill the tumor cells. There is another mechanism on the immune system. So the tumor cells are activating some chemical substance, the cytokine, and the cytokine have different effects. So there is a promotion, an activation of pro-tumoral cells, and there is also a shift of the immune cells which were acting against the tumor that become collaborative with the tumor. Okay, they are just changing their role. Okay, so you have an arrow in this direction and an arrow in that direction. The action of the pro-tumoral cells is to increase the growth rate of the tumor cells. Another action is like the pro-tumor cells are able to remove anti-tumor immune cells. Okay? So there are different arrows that you need to translate into different terms into the equation. So this is really a mess. I don't want to write the equation. Okay. What do we do with this complicated equation? What is interesting is to decide whether or not what we are doing can help in designing better treatment. So we are really far from that due to a lack of data, but at least it can guide the intuition. And there are two main ways to design treatments. One is to reduce the activation of the pro-tumor cells. Okay? One is to reduce this arrow which is here. Okay? So we have less pro-tumoral cells, which is good for the situation. Another way to design a treatment is to play with this arrow. As I told you, the pro-tumoral cells are removing anti-tumoral cells, but they do not kill these anti-tumoral cells, they just put them into a state where they are not able to fight against the tumor. So this is what we call the exhausted state. And there are treatments which are able to restore the activity of the exhausted cells. Okay? So we play with these two treatments in the equation. And what is interesting is to understand what is the role in this treatment of the time where you start the treatment and the strength of the dose that you are giving to the patient. So this is illustrated by the simulation which is here. Okay, let me comment the simulation. For the two first pictures, you have no treatment at all. Okay, so in this case, you see that the division rate is quite small. This is a good situation. The immune system is strong enough. It is able to control the growth of the tumor. Fine. You increase the division rate. So now this is really bad. You increase the division rate, and you are going to the escape phase where the tumor growth is completely under control, and this is really a bad situation. Okay. Here we start a treatment at time t = 5, and the strength of the dose is 1/2. Okay? And you see the treatment, there's one single treatment. Okay? I choose one of the two, and I see what happens. And you see that the treatment is efficient in the sense that it restores equilibrium, and the equilibrium value for the tumor mass is quite okay. Yeah?
In this case, Thierry, you have the A = 4, so it should have gone to escape, but with the treatment it does not?
Yes, okay, here the A is 1/4. Here the A is 4.
And the question on the microphone, please?
Ah.
Because we didn't get the question. You can repeat it.
Ah, okay, sorry. The question is about the value of the coefficient A in all the figure. Is that okay?
Yes, in the last one.
So in all the figure, this one and the three pictures on the bottom, the value of A is 4. Okay. So the value of A is 4. So here I start the treatment at t = 5, and the strength of the treatment is 1/2. And the treatment is efficient in the sense that we restore the equilibrium at the value of the tumor mass, which looks, let's say, reasonable. Okay. If I start the treatment a bit later, so here I start the treatment at time t = 10, and the dose here is 2. Okay, so I multiply the dose by 4. And this is not efficient enough because we are still in the escape phase where you cannot control the tumor growth. If I increase the tumor dose up to 5, I'm able to restore an equilibrium. So this is the situation. Okay, so the treatment starts at 10, like that, later than here. But the dose is 10th what it was here. Okay? And you are able to restore the equilibrium. But maybe it raises the issue of the toxicity of the treatment. So maybe you are killing the patient because the dose is too strong. And in the last picture, there's a situation where you start still the treatment at time 10, but you combine two treatments. And what you see is the fact that you are restoring the equilibrium with a value of the dose which remains quite low, which is exactly the same as here. Okay? So there is an interest in combining two treatments, both with respect to the administration time and in terms of dose. Okay, so let me finish with a few perspectives. So what we are doing now about that, we are just changing a little bit the modeling viewpoint. We are working with a more macroscopic model by dealing actually with reasoning from mixture theory. So this has been introduced actually by other people like Bain and Preciosi that we have seen yesterday. And this is a completely different viewpoint, but the interest is that now we have plenty of images produced by our collaborator in biology. And the goal, the challenge will be to compare the result of simulation with the image that you obtained by mass cytometry. So this is the PhD thesis of Christian Taillou-Fotso, which was here up to yesterday, and with Florence Hubert. So thank you for your attention.
Thank you. Thanks a lot for your presentation. So you assume diffusion of immune cells. I was wondering whether you think you could perform a mathematical analysis if you assume a more complex movement of immune cells, which in reality use an existing network, and you know, from the lymph node to the tumor site, it's not like direct line. So it's an open question about what you think could be done.
Okay, my first idea in that direction would be to play with a diffusion coefficient which is space dependent. This is not exactly what you are saying, but this is the first step in that direction, and I'm sure it would change the result. It would change the efficacy. If the diffusion is such that it's difficult to reach the tumor, even if you have the chemotaxis, I think it will have a strong impact on the solution. Again, the difficulty is the lack of data. It's already difficult to have a single value for D. So having a network is, yeah, I don't know.
Yeah, thank you for the presentation. I have a related question. I wondered how, so it's open question too, how the results are depending on the two-scale hypothesis that you mentioned at the beginning, because it depends what you want to look at, but you will never have your data for your whole body when you have a tumor localized at one point in the body. And do you think to change this hypothesis, or is it something that is really important in your results?
Okay, so as I told you, this modeling is very restricted to a specific phase of the tumor growth, which is certainly below the detection limit. And what we observe for the equilibrium, when we work with biological data as far as possible, is that really the tumor mass or the tumor size is very, very small. Okay, this is less than a micrometer, for instance, while the length square of the displacement of the immune cells is in centimeters. So it makes sense in this period. But of course, what you observe is something different. This is a later stage of the tumor growth, and this is why we are changing our viewpoint for the next step of the collaboration. And we are doing things with a model of fluid mechanics, let's say, that will be completely different. But it depends what you want to discuss.
Are there more questions in the audience? Okay, is there a question online?
I have one.
Please, go ahead.
I'm not sure I get the gain of the size structure for your tumor with respect to a standard growth model. What did you have data about the size distribution, or because at the end you only use the total mass?
Okay.
Of the interaction.
Okay, I presented the result with the total mass, but we have also access to the size distribution. Okay, and the size distribution, as far as it is possible to compare, makes sense to what we observe in the literature. Okay, so we have some.
So you have the size distribution of the,
absolutely.
Experimental.
Yes. Yes. It makes sense. Okay, I'm not saying that it coincides exactly with something with experimental data. It makes sense. It makes sense. We have something like that, for instance. Okay. Yes, we have adopted this viewpoint. First, because it coincides with the description that the biologists we were working with had in mind. Okay, we started the discussion that way. We were around the table and we were asking, okay, how do you see the phenomena? They describe the phenomena that way, and it imposes this set of equations. First. Second, this equation of growth and division is a quite well-established model that has been used, for instance, by Benoit and his collaborators for also cancer growth. Okay, this is a viewpoint. You can do something different. I completely agree with you.
And are there more questions online, or maybe one in the audience? Please, go ahead.
Follow up to the previous question. The fact that you have the size distribution might motivate you to experiment with it's a question I thought before. I think your immune cells act in the same way on cells of different sizes, right? But the effect of the immune cells might depend on the size of the cell.
Yes, not in the simulation, or the coefficient were constant, but it could be, yeah.
So, and the fact that you have the size distribution, that might be a way of doing something with it, right?
Yeah, sure. For the simulation, we can do many things. The question is what is the value of the parameter. So
Sure, I completely agree, but it's just a follow-up to the question before, right? Your main results, for your main results, the size distribution so far is not really very important.
Well, actually, I should say that, okay, for the simulation that I showed you at the end, well, we have plenty of very complex mechanisms, and we try to play with the case, for instance, where the growth rate is constant, and the case where the growth rate is driven by the compare slope. I should say it's not very convincing to change a model for another. So I would, if you are interested in the application, I would suggest to start with the thing as simple as possible.
I completely agree, yes. Can I ask another one?
Go ahead, go ahead.
In your model, the healthy state is always unstable. Do I understand that correctly?
Okay, what I said is in the case where you make plenty of simplifying assumption and you replace the PDE system by an ODE system, indeed we have an healthy case, an healthy state, and you can investigate the linear stability of the ODE system, and the healthy state is linearly unstable. This is exactly what I said. For the PDE system, I absolutely do not know.
Doesn't make me happy, right? I mean, that we are always full of tiny cancers.
Yeah.
Okay, more questions? So then let's thank Thierry.